I got a picture of an atom up on the board right now. I want you to label the picture of this atom so that we can move into our electricity unit with a little bit of background as to what makes up this atom, which of course ultimately is what allows us to have electricity. Tell me what this thing is in the middle there. What's that called? Yeah, that's a nucleus. And inside the nucleus, we have two things. I mean, we have lots of them sometimes, but we only have two different types of things in that nucleus. What are they? What's in the nucleus? Protons, and protons are positively charged, and we have neutrons. Neutrons are neutrally charged. Do you guys know what the mass of these things are? You don't need to remember the mass, but yeah. You know, you're thinking of charge. A proton is plus one. Plus ones usually we say for a charge. A neutron is zero or neutral. But mass, they both have a mass of about 1.67 times 10 to the minus 27 kilograms. So they're pretty light. They both have a mass that's almost the same. Not exactly. Okay, a neutron is actually a tiny bit heavier than a proton, but to 2 decimal places, it's the same mass as the proton has. So neutron, no charge, proton plus one, mass, both about the same. These things are pretty tightly bound to each other by something called the strong nuclear force. There's also an electric force that acts between proton and proton that wants to break this whole nucleus apart, but this strong nuclear force keeps this nucleus together. Bottom line is, under normal circumstances, these neutrons and protons don't go anywhere. These neutrons and protons will stay where they are. So under normal circumstances, talking about electricity certainly, the protons and neutrons don't really play much of a factor. Okay, what plays a factor? We're talking about electricity. It's going to be these things that orbit around the nucleus. And what are they? What are they called? Yeah, they're called the electrons. And sometimes there's 1 electron or 2 electrons. Sometimes there's 50 or even 100 electrons. These electrons have a charge of, protons are plus 1, electrons have a charge of minus 1. But they have a mass that's about 10 to the minus 31 kilograms. Much, 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 much lighter than the nucleus. Now, what's important to know about these electrons is that there is an electric force that acts on these electrons that keeps them in orbit, just like there's an electrostatic force that pushes the protons apart. The electric force keeps the electrons tied to the nucleus. It likes to push the protons apart, but that strong nuclear force that's stronger than the electric force that keeps the nucleus together isn't acting on these electrons. So this strong nuclear force, that's the strong force, doesn't act on these electrons. That means the electrons, although they're bound to the nucleus, aren't as tightly bound to the nucleus. So they can move. They can leave the atom. They can go, Ethan, from one atom to somewhere else. And it just takes a little bit of energy to do that. And that energy might come from literally rubbing two things together. Can provide enough energy sometimes for electrons to leave one atom and go somewhere else. If something's going to move under normal circumstances, it's going to be the electron. And that's going to be because they're not as tightly bound to the nucleus. Even though they're attracted to it, they're not as tightly bound to the nucleus as the protons and the neutrons are. If something moves, it's this. Okay? That's why we call this unit electricity. Electricity, because electrons can move. Electrons will move provided enough energy. So let's talk about a little bit more about the charge that comes from these atoms. Positive charge, we're not talking about just a proton. We know that a proton is positively charged, but usually when we're talking about positive charge, we're talking about an object that has positive charge. And it has lots of protons. It's also got lots of electrons. It doesn't just have protons. It's always got both, and neutrons as well. But what we're saying when an object is positively charged is that it has, less electrons. More protons than electrons. Or you could say less electrons than protons. How does it get that way? Well, there had to have been somehow electrons have left this object. It has less electrons, electrons have left. It doesn't mean that we've gained protons to give it more protons. Because remember, that doesn't happen. Protons stay where they are. You can't gain protons from anything. By the way, if number of protons change, that's not an electrical interaction. That's a nuclear reaction. And that can happen, but not under normal circumstances like we're talking about in this unit. You rub a balloon against your hair, you're not going to cause a nuclear reaction. You rub a balloon against your hair, electrons will leave and move around. That's an electrical interaction. And that's what happens. You rub the balloon against your hair. The electrons leave one, go to the other. Leave your hair, go to the balloon, or leave the balloon, go to your hair. The one that loses electrons becomes positive because it has more protons than electrons. The one that gains electrons becomes negative because a negatively charged object has more electrons than protons. And if you gain electrons, then you're going to have more of them than you have protons. Remember these two forces, this electric force, which tries to actually break apart the nucleus, but keeps the atom together. And then the strong nuclear force, which is over small distances, stronger, but it doesn't act on the electrons. So it's really, really strong inside the nucleus and keeps that together and keeps the protons and neutrons from leaving and going somewhere else. More so than the electric force keeps the electrons in orbit around the nucleus. It does a pretty good job of that, but all you got to do is rub that balloon against your hair, and all of a sudden you can overcome that force. You can put enough energy into it to cause that force to break on some of the electrons. Some of the electrons will leave. All right? Something's going to move. It's going to be the electrons. The unit of charge is called the coulomb. Just like the unit for speed would be meters per second, the unit for energy would be joules. The unit for momentum in our last unit was Newton seconds or kilograms meters per second. The unit for charge is coulomb. That's a brand new unit for you. I don't think you've probably ever heard that before. Maybe in chemistry. Some of you? No? Now, for perspective, I'm going to tell you that in order to get 1 coulomb charge, a coulomb is a big unit of charge. Okay, like you guys know that a light year measures distance. Okay? The distance that light travels in 1 year. That's a really, really big unit of distance. And occasionally we use that unit because it's convenient when we're talking about some far off star or something like that. But a lot of times we don't use it because it's not convenient. It's more convenient to use a meter or a kilometer for unit of distance. Bottom line is, if we use a light year, it's a really, really big unit of distance. A millimeter is a really, really small unit of distance. A coulomb is a big unit. And to give you a perspective as to how big it is, you would need about this many electrons to have a full coulomb of charge. About, give or take. About 10 to the 19 electrons to make up 1 coulomb of charge. That's a lot of electrons. That's a lot of electrons. That tells us that a coulomb of charge is a lot of charge. Most times we see a problem involving coulombs, honestly, we don't see a full coulomb. We see microcoulombs or nanocoulombs, 10 to the minus 6 or 10 to the minus 9 coulombs. Because if you have a coulomb, it's a big, big unit of charge. Just like a light year is a big, big unit of distance, right? You don't have to remember exactly how many electrons make up a proton, just that there's a lot, because the unit is a big unit. Let's look specifically at the exact charge of an electron or proton. What I want you to do here, guys, is check your data sheet. Look on your data sheet, because it's on there, but it's a little bit hard to find on your data sheet, so I want to point that out to you, okay? Look at your data sheet. The part of the data sheet that looks like this. You're going to see in the top right-hand corner, you've got this list of particles, alpha particles, electrons, protons, neutrons, and these first-generation fermions, which are positrons and neutrinos. We got some charges listed. We got some masses listed. You can see the alpha particle is pretty light, but pretty heavy compared to an electron, right? About 1,000 times heavier or so. Proton is in the order of magnitude of the alpha particle, much, much heavier than the electron. That's easy because it's given to us in kilograms. But look at the charge. We're told that an alpha particle is plus 2e, or an electron is minus 1e, or a proton is plus 1e. What's the e mean? Yeah. Yeah, it's the elementary charge over here. So we're going to say that an alpha particle would be 2 times 1.6 times 10 to the minus 19 coulombs, or 3.2. An electron would be negative 1.6 times 10 to the minus 19, and a proton would be positive 1.6 times 10 to the minus 19 coulombs. You don't need to memorize those numbers because they're on your data sheet, but be aware of where to find them, because you got to look at 2 places, right? Charge of an electron, negative 1.60 times 10 to the minus 19 coulombs, which is negative 1 times this mysterious elementary charge we'll talk about in our last unit. Proton is positive 1.60 times 10 to the minus 19 coulombs, which is plus 1e. Positive 1 times this mysterious elementary charge. We'll learn exactly what that elementary charge is later on this year, but for now, let's just go with it. Let's define a couple of more terms now. You guys ever heard these terms before, a conductor and an insulator? In, I believe it was Science 8, maybe Science 9, you guys would have learned about heat. And you would have learned about heat conduction. Okay? Metals tend to be good conductors of heat. They tend to be good conductors of heat, right? Something like fiberglass or even air is actually a pretty poor conductor of heat. In other words, it's an insulator. It's a pretty good insulator, right? We're not talking about conductors and insulators in the context of heat. We're talking about conductors and insulators in the context of electricity. But let's think about it in the context of heat for a second. A conductor in the context of heat allows heat to flow from one place to the other, right? If you can conduct heat, then it moves from one place to the other. Okay, if you have a flame on one burner on your barbecue on one side of the barbecue, but yet you put your hand on the other end of the barbecue, you'll burn your hand because the metal in the barbecue is a good conductor of heat. The heat transfers through that metal to the other end pretty quickly, and you'll burn your hand, right? Whereas if that barbecue is made out of something that wasn't such a good conductor, like plastic, some flame-resistant plastic, then you could touch the other end of the barbecue, right? You put a stove on the, or you put a stove on the pot. Yeah, put a pot on the stove, and you usually have a plastic or wooden handle, right? Because it insulates. It doesn't transfer heat very well. We're talking about electricity. A conductor would be a material that allows electrons to flow. And why does it allow electrons to flow? Well, because the electrons in the outermost regions of the atom aren't that tightly bound to the atom. The electrons can be easily removed from the atom. Can you give me an example of something that has, chemistry people will know this. Give me an example of something that has electrons in the outermost regions not that tightly bound to the nucleus. Even a general category. Metals, right? Metals tend to have electrons that aren't as tightly bound to the nucleus. They're more free to move. That's why metals tend to be good conductors. Now, some metals are better conductors than others, but they tend to be better conductors than, say, something that's a non-metal. A piece of wood will conduct electricity, but not nearly as well as a piece of metal. Air will conduct electricity. Right? Lightning forms in a cloud and goes all the way to the ground. Air will conduct electricity quite well sometimes, but not nearly as good as metal. By the way, why does lightning usually form when it's damp as opposed to when it's dry? Like you don't see lightning when it's sunny outside usually, right? You almost never see lightning in the winter. It's possible, but you almost never see it. Anyway, big snowstorm. Why don't you get lightning in a big snowstorm? Yeah. Yeah, water is a much better conductor than air is. So if you get humidity in the air, those hot, humid summer days, what happens? You get a lightning storm, right? Those rainstorms, you get a lightning storm. But if it's dry, like it is in the wintertime, especially in Alberta, then you don't get lightning because the air isn't a good enough conductor to transfer the electrons from the cloud to the ground. Air is a pretty good insulator, but it can be a better conductor if it's got moisture in it. The insulator, we're going to say, is a material which the electrons are pretty tightly bound to the nucleus and therefore not free to move around within the substance. Again, it's not to say that they can't move. It's just harder. It's not like here's your conductors and here's your insulators as complete separate categories. There's a continuum. You go from really, really good conductors to gradually not as good of a conductor to gradually things that don't conduct very well at all. It's kind of hard to define the border between conductors and insulators. It's a little bit arbitrary. You don't have to copy down this next page. This is just basically a diagram for reference. It tells you examples of conductors, examples of insulators, and how good of a conductor something is and how poor of a conductor something is. There's numbers along the side here, but these numbers aren't values with any kind of units that tells you how good of a conductor something is. Rather, the relative values. So let's say something has a conductivity of 1. Well, if something else has a conductivity of 10, we don't have any units for that, but we know that it's 10 times better than 1, right? We're talking about things like silver and copper and aluminum. Okay? These are 10 to the 8, like 10 to the 8 relative to, I mean, carbon is a decent conductor, but we're talking about 10 to the 5 times better, about 10,000 times better than carbon would be as a conductor. So there's like much variation even within things that we consider to be conductors. And then we go down here to things like wood and glass and rubber, 10 to the minus 10, 10 to the minus 15. Look, silver is 10 to the 23 times better of a conductor than rubber is. Like, that's a lot. Doesn't mean that rubber won't conduct electricity. It will. Hopefully you never get struck by lightning. But let me tell you, if you do, wearing rubber-soled shoes will make very little difference. Even though the rubber in your shoes is an insulator, it'll still conduct electricity, especially when you have something like lightning. Just not nearly as well as, say you happen to be out golfing and holding a metal stick in your hand up into the air. That'll conduct it a lot better than your shoes will. Yep. One would be in here in this region here where we call semiconductors. So I can't give you a material that's exactly 1, like 10 to the 0. But basically, we'd say it's kind of a transition from conductors to insulators. Basically, I guess you'd say, look, if you're 10 to the something positive something, you'd be pretty much safe to say we classify it as a conductor. 10 to the minus something, we'd consider it to be an insulator. But again, it's a little bit arbitrary where you define that, right? Copper is a really, really good conductor. That's why we use copper for wires, right? We make wires out of copper. So is aluminum, by the way. Aluminum is a really good conductor as well. Your house would be wired with copper, but houses used to be wired with aluminum wiring. Not anymore. Not because it's not a good conductor, because it is. But aluminum tends to, yeah, no, it doesn't rust. It's good that way, actually. No, actually, copper is very expensive, actually. Over the last 10 or 12 years, copper has gotten, like, crazy expensive. Like, so much so that there's actually, like, people that steal copper and then sell it. Like, sell copper to be melted down and whatever. Like seriously, like, literally, it's happened. You hear these stories every once in a while of this manhole cover that somebody found off one morning, and then when the power company comes, they realize, oh, all this copper wiring underground was stolen through the middle of the night. Okay? People have been electrocuted doing that before. killed trying to steal copper because copper is so expensive. That's only been the last dozen years or so, though. Copper is a really good conductor. So is aluminum. Aluminum is not more expensive than copper. Yeah, aluminum tends to arc, actually. Like when you have two aluminum wires, electrons will tend to arc from one piece of aluminum to the other better than they will copper. So that's why we stopped using it in houses, aluminum wiring, is because when you got wires in your house, you don't want electrons to be arcing from one wire to the other because it leads to fire, right? Your house burning down. Yep. No, copper would be a better conductor than aluminum, but they're in the same order of magnitude, so they're close. I'm not sure. That's a good question. I'm not sure why that would be. Okay, yeah, I'm not sure the answer to that actually. It's a good question, but look it up. I'm sure you can find it somewhere. Okay, don't worry about these numbers, guys, but do remember that things like, metals, right, are good conductors, and things like wood and glass and rubber are bad conductors, or in other words, insulators, good insulators. If it's a good conductor, it's a bad insulator. If it's a good insulator, it's a bad conductor. All right, we're not going to do much else here today in terms of new stuff. I'm going to give you 3 laws, though, that describe electricity, 3 basic laws. You guys have heard these before. In fact, you've done electricity in Science 9, I think it is. Just not to the kind of detail we will this year. You would have learned these rules, though, or these laws. Yep. Yep. Opposite charges attract. What that means is positive attracts negative and negative attracts positive. If you have a balloon that's negatively charged and you have something else that's positively charged, your hair that's positively charged, then the balloon will be attracted to your hair. Like charges repel. What does repel mean? I used to just give you this rule and say, yeah, like charges repel. Positive repels positive, negative repels negative. And then I move on to the next one. But then somebody asked me one time, what does repel mean? It's like, well, this doesn't make any sense at all if you don't know what the word repel means, right? What does repel mean? Okay. Yeah, push away. So if you have positive, it pushes away positive. It repels positive. It won't come together, they push away. And negative repels negative. Peter? So if you bring 2 negative charges close together, what force? The electric force. It's similar to gravity, except it can be attractive or repulsive, whereas gravity can only be attractive. It's also a stronger force than gravity is. But similar in nature in terms of how it acts. It acts over a distance. Okay, it acts over a distance, and it's inversely related to the square of the distance separating them. So that means as you get closer and closer and closer, the force becomes bigger, bigger, and bigger. Okay, does that make sense? So it's no problem to bring 2 negative things like this, but as you get closer and closer and closer, it becomes harder and harder and harder to push them in because that force of repulsion is bigger. Similarly, though, if you have opposite charges, as you get closer and closer and closer, it's harder to keep them apart because they attract each other more, right? Just like, okay, if you happen to be on Earth, you're attracted to Earth fairly strongly. If you happen to be in space, you're not attracted to Earth that strongly because you're further away, right? The closer they are, the bigger the force is.